Okay, today's lesson is section 7.3. We're going to discuss some more operations with radical expressions. Last section we discussed multiplying them. Today we will discuss dividing, adding, and subtracting them. Why don't you go ahead and pause the video, try these warm-ups. Okay, go ahead and see how you did on these warm-ups. Only thing I'd like to point out is to make sure you remember to use absolute value brackets anytime you pull out a variable from an even and indexed radical. Okay, here's our quotient rule of radicals, very similar to our product rule of radicals. If you want to look back at that, it basically just says if you're dividing two radicals that have the same index, then you can go back and write it as a single radical with that same index and then just divide the radicands. Only restriction here is that b is not equal to 0 so that we don't get 0 in the denominator. So something like the cube root of 27 over 125, just break it up as two different radicals, the quotient of two radicals. Take the cube root of each, you end up getting 3/5. Same thing in letter B will be the square root of 25 over the square root of y squared. 5 over the absolute value of y. Letter C, square root of the numerator, which is 16x cubed, over the square root of the denominator, which is y to the 4th. Square root of 16 is 4. 2 goes into 3 one time with 1 left over. X goes into absolute value brackets since the index is even. 2 goes into 4 two times. Bring out 2 of those y's, nothing left, goes into absolute value brackets. Letter D, cube root of the numerator over cube root of the denominator. Remember, we're not going to use absolute value when the index is even, or even when it's odd. Cube root of 27 is 3. 3 goes into 5 one time with 2 left over underneath the cube root. Denominator, cube root of 343 is 7. 3 goes into 3 one time. Bring out one of those x's, no absolute value brackets. Now, when you look at example 2, you'll see we're going to go the other way with it. In example 1, we had the quotient underneath one radical, and we first broke it up into the quotient of two radicals. In example 2, we're going to go the other way with it. We're given the quotient of two radicals, and we're going to write it as a radical with just the quotient underneath one radical. Now, I did this a different way first, the longer way of doing it, to see that it still works that way, but you'll see it might be better to use our quotient rule, and since both of these square roots have the same index of 2, just write it under one square root, 80 over 5, which is 16. Square root of 16 is 4. Again, the 5 stays. Cube root, dividing two cube roots, I can make it a single cube root of 32 over 2. This is 5 times the cube root of 16. Now I simplify the cube root of 16 by a method of my choice, whether I like the factor tree method or if I like to find the largest perfect cube that goes into 16, which is 8. Cube root of 8 is 2. 2 times 5 is 10. I'm left with 10 times the cube root of 2. And finally, write this under 1/4 root. I'd be left with the 4th root of 32 a to the 5th b to the 3rd over 2b to the negative 1. Simplify underneath the 4th root. Underneath the radical, using my properties of exponents, I would get 4th root of 16 a to the 5th. Subtracting exponents, I get b to the 4th. 4th root of 16 is 2. 4 goes into 5 one time with 1 left over. 4 goes into 4 one time. These variables can go into absolute value brackets, and the a stays underneath the 4th root. Okay, why don't you go ahead and pause the video and see how you can do on these checkpoints. Okay, go ahead and see how you did on these warm-ups, and then we will move on to adding and subtracting radicals. Now here it is explained that any two numbers can be added. Okay, so 7 and square root of 3, they can be added, and you would just write it like this. You cannot simplify that anymore. However, if you have like radical terms, then you can simplify that more. Like radicals are radicals that have the same index and the same radicand. And when we have that, we collect them as if we were just collecting like terms here, like in 6x plus 4x. We know we get 10x. A different way of looking at this that might help you is look at this as the distributive property. We can factor out an x. You're left with 6 plus 4, which is 10. And that is how you get to 10x. Looking at letter B, this is the exact same problem, but instead of using x, we now have square root of 7s. Both of these radicals have an index of 2, and they have a radicand of 7. So I can factor out the square root of 7, and I just add the 6 and the 4, the coefficients. So you get 10 times the square root of 7. Letter C, we have 3 radicals. They are like radicals because they all have the same index of 3 and the same radicand of 2. So factor out that 2, or the cube root of 2. You're left with 8 minus 7x plus 5. Keep that in parentheses because if you didn't, then this multiplication would be done first. And we don't want that. We need all of these coefficients to be added and subtracted first. So you need to use the parentheses here. I have some like terms to collect in here. 8 plus 5 is 13, so I'd be left with, in standard form, negative 7x plus 13, keeping that in parentheses, times the cube root of 2. The next example, we actually only have 2 like terms here. 2 like radicals. Not here because the index of 3 is different. So that's just going to stay. I can collect these, though, into 10 times the 5th root of 4x minus 5 times the cube root of 4x. And that's all you can take it from there. Now letters E and F are a little different. They're a little bit tougher because it may appear as though you can't do anything because you don't have like radicals because the radicands are different, 8 and 2. However, square root of 8 simplifies. As we've seen in previous sections, you can either use your factor tree method or find the largest perfect square that goes into it, which is 4, 2 times. And everything else can stay the same. So 3 times minus 5 times the square root of 2. 3 times the square root of 4. Well, since the square root of 4 is 2, 3 times 2 is 6 times the square root of 2 minus 5 times the square root of 2. Now you can see we have like radicals. Same index of 2, same radicand of 2. 6 minus 5 is 1, so you're just left with the square root of 2. So sometimes you have to actually simplify the radical to get like radicals. Like here, if you simplified the cube root of 16y to the 4th, you would end up getting 2y times the cube root of 2y. Everything else would stay the same. 5 times plus 7 times the cube root of 2y. Now we have like radicals in the cube root of 2y's. 5 times 2y is 10y times the cube root of 2y plus 7 times the cube root of 2y. I can factor out my like radical of cube root of 2y, and I can add my coefficients. Now, since these coefficients are not like terms, I can't call that 17. I just have to call it 10y plus 7. And since there's more than one term, I need to keep it in parentheses to indicate that that addition needs to be done first before this multiplication. Okay, go ahead and finish off these checkpoint problems. Pause and see how you can do. Okay. Go ahead and see how you did on these checkpoints. And finally, we have the closing question. Go ahead and see how you can do with this little word problem. Okay, this closing question was really just an example of how a radical function could be used. So all you had to do here is plug in 8,820 for L and evaluate. And finally is your homework. It's the next worksheet in your packet, numbers 1 through 16 all.